you get mass divided by volume, which is density, G H, which is the same as projective. Okay? So that is pressure. But just with the pressure, it's not enough for a pan to absorb, to suck the water up to the tip of the top of it. The reason that a tree can have water all the way up, like 70 meters, is because there's stoma and the opening will create a small radius. At this small radius, the water surface is touching a circumference, which causes surface tension. The surface tension will then cause a force equals the surface tension times the circumference, 2 pi r. Okay? Assuming that this angle is like 90 degrees. But you know it should be proportional to the radius. But this is force. The key to have water height is pressure. So to get pressure, you divide this force with area, which is going to be pi r squared for a circle. Then you get this gamma, 2 pi, it's going to be 2 gamma divided by r. My gamma is the same. Gamma. That's not so much adding. You see that even though the capillary force is proportional to radius, the capillary pressure is proportional to 1 over radius. So the smaller the opening, the bigger the pressure, and a tree can have water all the way to the top of it. Okay? That's surface tension. Any questions? I got energy. All right. Now let's go to momentum. Momentum is about the motion. We have conserved momentum, which equals mass times velocity. So when things are colliding into each other, you compute the initial momentum and final momentum, add them together, you'll see that it's the same. To change momentum, you need impulse. And you see it turns out to be mass times acceleration times the change of time if force is a constant. So impulse is going to be force times how long you push something. If you have a system, the formula is easy. When you add all the momentums, you find that the expression is the same as the numerator of center of mass velocity. So you know it's just the total mass times the velocity of center of mass. And if you want to change the total momentum, you find that the total impulse will be the sum of external force times delta t plus the sum of internal force delta t. And you see that the internal force will cancel because they are both multiplied by time. Impulse is force times the change of time. The change of time is the same for every particle. So you can just take it out of the parentheses and then cancel all the internal force. So the impulse acting on the system end up being just the external force times delta t. So as long as the external force or the external impulse is zero, there will be no change in momentum. That's why the particles can interact with each other. They can bounce into each other and go away. There's internal impulse, but if you add them, they cancel. So as long as there's nothing outside the system doing impulse to the system, then the momentum of the system will be conserved. Okay? So that's basically all for momentum conservation. It's like sure. Any question? Alright, so when we go to rotation, we need to go back to energy. First, we look at how exactly should we rotate an object. We find that if you have a seesaw like this and you want to rotate it, let's say initially it is down here, and there is a block on the top. So the block will change a height h, which means your energy increase by energy h. Now, this energy is not free. You need to do external work to increase the energy of the system. And that work comes from you pushing down, and you need to take the component along the displacement. So if this is theta, which is the angle between your lever arm and the force, you need to take the sine theta, and that will be the component along the displacement that will do work. So if you go down by d, this distance down is d, then the work you've done will be the component along the displacement times the displacement. Any questions so far? I hope you done this in your homework test now. Alright, so if you are using just enough force to lift the block, then there's only going to be the potential energy change. The kinetic energy will not increase because you are giving just enough force to lift out the object slowly. So the work you've done goes all into the change of potential energy, and you have f sine theta times the distance you push equals energy h. Now, if you have a shorter lever arm, then the distance you push down will be shorter. But the increase of energy is the same because no matter how short your lever arm is, the height change of the block from on the other side of the seesaw is the same. So to do the same amount of work with shorter displacement, you need bigger force. So you know the force required to lift the block depends on the length of the lever arm. If the lever arm is longer, you can have a longer distance to do the work, and the amount of force you need is smaller. If you have a shorter lever arm, you need to increase the energy by doing a small displacement, and that requires a big force to create the same amount of energy. Therefore, you know when you're rotating something, the key is not force. it's force times lever arm. You can see that by this triangle, the lever arm of the block is L, and the lever arm of U is R. This angle is going to be the same. So you have D equals R theta and F equals L theta. Any question with those two? We are assuming angle is small, so you can just approximate the height as the arc of the slice of pizza. So plugging in here, you have F sine R, or let's call it phi. So we don't confuse that theta with this theta. Equals mg, h will be the lever arm times the angle. And you see the angle cancels, and the result becomes the lever arm times the force times this factor of sine equals mgl. So this is when you are applying just enough force to lift up the object. If you just want to lift up the object, the criteria becomes bigger. You just apply bigger force. Okay? So we see for rotation, what governs the rotation is not force. It's this combination between lever arm, force, and sine theta, which comes from energy conservation. And therefore, we call that thing torque, denoted by tau. Torque is what causes rotation. Okay? So if you just want to ask which direction will the object start rotating, you just need to sum up all the force, all the torque. Let's say you have any object trying to rotate around the pivot. So a force acting on this point will have a lever arm from the pivot to this point. The point that the object is acting on is important.